RhinoCAM can provide. One is 2.5D for the uninitiated. If I just have a couple of circles here and a couple of rectangles, I can use those commands to just make a pocket into that into those shapes, and I can define the depths. But the outline is pretty much all I need for those operations. Also, V-carving, you've seen in the beginning of my presentation that door segment I made. This is actually generated with the V-carving routines from MecSoft. Then I have the 3D strategies, which are very, very complete. I encourage you to go to the MecSoft website and download the manuals, because the strategies are listed there. And we have the 4D, which is like working like a gyro spit, basically, to carve something out of a rotating axis. And then we have drilling operations, which allow me to to chuck a drill into the collet of my spindle and then drill deep holes, for example, while the drilling is slowly advancing up and down. Those are the basic strategies. In our case, we keep it simple again. We can spend the whole day in discussing different strategies. And we'll just take a so-called parallel finishing path, which is opening here. I can select machining regions, and I have defined a simple curve, a rectangle around this piece, which is then defining the region RhinoCAM should look at. This could be a very big part with lots of different segments, and with a curve around a focus, it allows me to specify which part of my big project I want to machine. So this is defining where it should look at. Then I can define a tool, which is a 1/16 of an inch tool here, already prepared. Flute lengths, tool holder, diameters and stuff. RhinoCAM is able to provide information. If you cut very deep and very complex passes, then it will show you where your spindle would collide with existing geometry if you fill in this with meaningful parameters. Tools. There's I didn't show this, but it doesn't look like it here, but there is a big tool library, a management system behind this, which allows you to keep your zoo of different cutting tools organized and then load them here as necessary. For smaller projects, I must say that I'm guilty of just entering them every time. I'm not loading it. I'm not really utilizing that a lot, but it's there. If you're a bigger shop, then you can organize everything. Then here with feeds and speeds, I can tell the system the spindle speed, how fast the cutting spindle should rotate while cutting. Then I have the different speeds for plunge, approach, engage. Here are different color segments. This is the plunge part, so I can have it very quickly go down. Then I can sneak up on the material, slowly engage, and then speed up to the cutting. I can control this very fine. Again, using a very brittle, small, tiny tool with a big, mean machine makes it necessary to fine-tune this. Otherwise, you end up with a pile of broken tools. And this is obviously a typo because the retraction can be very fast. And that's the feed and speed. Entry and exit, I can control how the cutting tool descends into the workpiece on an angle, in a radial motion, or simply straight up and down. I have it set straight up and down. Specifically with metal cutting, having this is essential because some cutting tools do not allow you to plunge straight down, and then it is necessary to have the control over so-called engage motions. You will see in a second live what that means. Z containment means where is the top of my material. Here I can set all sorts of safe distances so cutting tools do not run into materials. Then the cut parameters are important. This here specifies how close I keep to the stay to the geometry. Sometimes there are reasons for roughing or for finishing not to be too accurate or to be very, very, very accurate. Then cut direction is a very interesting point. You know, the cutting tool only rotates in one direction, and here you can control which way the cutting tool is presented to the material, only in one direction all the time, or mixed in both directions, backwards and forwards. If you have very brittle materials like Macassar ebony in woodworking or palm wood, then it is very, very good if you can control this to minimize blowout. And in metalworking, you can determine the tool marks maybe you may leave. Then start side, you can determine which corner of the piece you will start with your tool pass. You can see here the direction as a start point changing. And here, angle of cuts is a very, very important part in woodworking, specifically when we make our life easy here. In just using one method to cut the entire piece. Angle of cuts, I'll set this to 45 degrees right away, because if the cutting tool would go back and forth to cut out the shape through solid material, if it would dive in here and it would cut over there, it would be broken till it's here, because it would have to dig an enormously deep trench with a very, very small tool, and the probability is very high that there is a little piece of material wedging in and just snapping it off. What we will do with a 45-degree cut is we will sink in here and basically like a drill, and the first move already which we will create will be a step to the front and a line to the back. However small it is, it already has a gap to the back, which will only grow further and further as we go in. So again, MecSoft to the rescue. It allows us to define those things. And here the step over control. How big are the steps we're going to make to carve with the tool to carve out the geometry here. So the finer this is, the longer it will take, the better the result is. The coarser it is, the coarser it will look, and the faster it is. And as it is in real life, it's like a budget thing. How nice do you want to have it look in which time available? So in metalworking, this has more tighter tolerances because of the forces acting on the machine bit. In woodworking, we go anywhere between 45 and 3%, and don't care much about anything else. And I think 25% with the distance we do here in aluminum would just end the bit right away. So good. Long story short, this is pretty much everything we have to check and set, and then I can say generate. It flickers around, and what we see here is the tool pass superseded to the on top of the geometry. The turquoise lines are actually the flight path, if you want to name it like this, of the tool. And if I zoom in here, you can see the yellow line, which goes right into the material. Basically, as I said, drills in, goes over, steps up, steps back, goes over, steps up, steps back, and so on, till it is finished on the other side and retracts here. So I can now check the tool pass itself, which gives me information about where it goes. I can check roughly the values and see, okay, this is not 30 feet in the ground. Don't believe me, it can happen. And RPMs, everything looks good. And there are also information which are very valuable and fairly accurate regarding the times it will take to machine the part. This is about 35 minutes. Rest assured, you will not have to look 35 minutes at a video. We sped this up. If I would say, oh, this is not something I expected, I know this part only should cut in half the time, I can check again feeds and speeds, because this is most likely the part where I made an error. I can go like to 600 inch per minute, which I could certainly do with a little bit more of a bigger cutter, and generate it again, and I see, the whole thing can be cut in 5 minutes. And it can be cut in 5 minutes, just not that pretty. Then there are a couple of functions which are really cool. I can transform the toolpath, reverse it,